Hmm. So this is chapter number 5, and we are dealing with additional analysis techniques. So there are furthermore analysis about circuit. We will be doing that. Okay. So let's start. Okay, so first I will draw equivalent circuit. I think we have done these circuits in the previous chapters as well. So you know that we all the time use voltage source and the current source as an equivalent, they are not exactly the same sources, but they are sources that we have used before, right? So we can say so what will be the V naught voltage here? What do you think?
Vs.
Right. V naught is Vs. And if we draw an equivalent circuit of this circuit in terms of current source, it will be something like this. And in this case, if it is the same R, the same IS is flowing, and V naught here will be ISR. So they both are equivalent circuits or interchangeable circuits when we are dealing with voltage source and the current source. So we just want to keep this information in our mind, and then we will go from there. Another thing I want to mention is that linearity of the circuits. So in this course, till now, we dealt with only linear circuits. Linear circuits are that if you increase one, the other will increase because the equation is linear. So in the linear circuits, characteristics, there are many characteristics of linear circuit, but two characteristics we will use here. One is scaling and other is additivity. So scaling is what? Scaling is like if you multiply one voltage by 2, the other voltage will automatically be multiplied by 2 because it's a linear circuit, right? And similarly, additivity is that if you want to add two currents, two sources, they will be equal to their equivalent. They will be equal to the sum of the currents or voltage. So we will say how this will work for our case. Okay. So first of all, let's try to scale the circuit. Okay. So scale the circuit. For scaling the circuit, I'm assuming V naught is equals to 1 volt. It may be or may not be equals to 1 volt, But here I am just assuming that V out or V naught is 1 volt. Okay. So the circuit here is okay. So do you think same I2 is flowing through 2 kiloohms and 4 kiloohms?
Yes.
Yes. Okay. So we have assumed that V out, V2, V naught, or whatever you call it, is 1 volts. Okay. So then our I2 will be V2 over 2 kilo ohms, and it's 0.5 milliamps because our V2 is 1 volts. Then the same I2 is flowing through 4 kilo ohm. So our V1 I can write as 4K I2 plus 1 volts, right? So that will make it so V1 is 3 volts. What is V1? This voltage or this voltage. Sounds good?
Yep.
Okay. Now I can find I1, and my I1 is V1 by 3 kilo ohms, and that will make it 1 milliamps. Okay, and so the current here, that is I, will be equal to I1 plus I2, right? And then it will be equal to 1 plus 0.5, which will make it 1.5 milliamps I. So I just want to confirm that VA here, which is input voltage, whether I'm getting the same VA with 1 volts at the output voltage or not. If I'm getting, then of course V naught is 1 volt. If I'm not getting the same VA, then it means that I have to scale my V out. Okay, so let's see. Okay, so how can I find now a VA? Now I know my I.
I times 2 kiloohms.
Okay, anyone else?
VA minus V1 equals I times 2 kiloohms.
Wouldn't it just be 12 volts?
We know that it's 12 volts. I'm just checking through my calculation that it's 12 volts or not. So now I know my I, right? I want to know, using my calculations, forget about 12 volts. Using my calculation, I want to know how can I calculate VA. Okay, so VA is actually, I know it's 12 volts, okay? But if this is a black box, and I don't know what's in the black box, then how can I find VA? I will say that this VA is the voltage drop here plus voltage here, right? Am I right?
Yes.
Ye-
Because if whenever you, let's say, apply nodal analysis here, you always say V1 minus 12 divided by 2, right? So it means that this VA is actually equal to voltage drop here plus voltage here, because the voltage here is the same as voltage in this branch and this in this branch. So there are no further voltage we have to add. It's just V1 plus the voltage drop here. So let's see. VA is equal to 2KI plus V1. So it will be so it will be 2KI plus V1. 2 into 1.5 is what? 3. And V1 is 3, so it is 6 volts. So VA is 6 volts. Okay, which suggests that with my calculations, assuming V naught is equals to 1 volt, I am getting VA is equals to 6 volts, which is half of the voltage than the original voltage, right? Is that true?
Yep.
So what it tells me that what could be V2 that I can get the 12 volts at the input?
Should be 2 volts.
Yes, it should be 2 volts, right? Because we are saying that these are linear equations, we can scale them. So if I am getting here 1 volt and my VA is 12 volts, so to get VA is equals to 6 volt, no, sorry, VA is 6 volts. To get VA is equals to 12 volts, I should scale it to 2 volts. Okay? Is it fine?
Yeah, that makes sense.
So it means that, it means that in linear properties, in linear circuits, in linear equation, we can scale them. So make it VA is 12 volts means that your V naught is 2 volts actually, because it's the linear, what you should say, linear property of the linear circuits. Sounds good? Makes sense?
Yeah.
I have a question. Once you scale that to 2 volts, then what does anything else change within the circuit? Like, what does that affect?
Okay, so we did not calculate V naught first, right? We just assume V naught as 1 volt, right? So the currents that we have calculated using our assumptions are not the actual currents, right? They are just the current that we got from our assumptions. So the actual currents are the currents which should come with the right VA, right?
Right. Okay. Thank you. That makes
So
sense.
Yeah, because these are all the assumptions, but we are just saying that it's all about scaling when they are linear equations. Okay. Okay, so we did scaling. Why I introduced scaling, we will know it later. But now I want to introduce another principle, that is additivity or superposition. Okay. So what is additivity or superposition? Okay. So principle of superposition suggests that we should simplify the circuit by reducing number of sources. Okay. We cannot just reduce number of sources like that if there are multiple number of independent sources in the circuit. So how can we reduce number of independent sources? We are just talking about for independent sources now. So they can be current or voltage. So the superposition principle can be defined as in any linear circuit containing multiple independent sources, the current or voltage at any point in the network may be calculated as algebraic sum of individual contribution of each source acting alone, which means that let's say you have I and V in the circuit, right? I means that you have current source, independent current source I, and you have independent voltage source V. So they both are at the same time present in the circuit. So when you solve the circuit, you take effect of both. But it says, the superposition principle says that you can also find out individual effect and then sum them up, and that should be equal to the combined effect. Okay. How it will work, we will see that too. So let's see. Okay. So what we normally do, I am saying that if there are two sources, let's say voltage source and the current source, to know the effect of only one source, I have to nullify the other source, right? So if I want to know the effect of voltage source, I have to nullify current source. If I want to know the effect of current source, I have to nullify the voltage source. So nullifying sources, how can we do that? Okay, so let's say that you have this circuit here and you have this voltage source and there is circuit here. We don't know what is this. Okay, there is a voltage source here. I want to nullify its effect. I want to say that there was no voltage source there. So what I want to do, I want to make this V is equal to 0. So which means, what should I do here to make V is equals to 0?
could you put another voltage source of like the same magnitude in the opposite direction?
Yeah, that's another thing. But I just don't want to introduce any other source too. But I just want to say that I want the circuit current running, but I don't want voltage source here. So I want to make it 0. Any other idea? What should I do?
Do you decrease or eliminate the resistors?
No, I cannot change the configuration of my circuit, but I can remove this voltage source. But if I want to remove this voltage source, I just say that V is equals to 0, taking this voltage source out and just connecting it with the wire or short circuiting the circuit. Short circuiting doesn't mean short circuiting the whole circuit, but short circuiting that part where the voltage source was. Okay?
Okay.
So that will make my voltage source 0 here, right? Why I am making it 0? Because maybe I want to know the effect of another voltage source, or I want to know the effect of current source, which is already in the circuit. So I am just trying to, can you hear me?
Yeah.
Yep.
I am just trying to nullify the voltage source. How can I nullify current source? Let's see. Okay. So this is my current source. Let's say I want to nullify its contribution. What should I do? Nullifying means that I should be 0. This current should not provide anything to this circuit.
Do you do the same thing? Do you short that branch where the source is in?
Okay. Okay. If I short it, right, I said that I want I is equals to 0. But instead of making I is equals to 0, it will create another part of the current in this circuit, and there will be no current here. I just don't want to change any other configuration of the circuit, right? So if I short it, it will just change the circuit altogether, and all the current will flow here. Instead of nullifying the effect, I am increasing the effect. Right? So what else I can do?
Could you make it an open circuit?
Yes, I should make it an open circuit, because making it an open circuit will nullify the effect of current source. So it means that I should open circuit the current source, or where the current source was. Okay, so I'm just saying that how can we nullify the source effect, right? So to nullify the effect of voltage, we will make it short circuit, not short circuit the whole circuit, but just the path where the voltage source was. And to nullify the effect of current, we will do the open circuit at that point. Does it make sense?
Yeah.
Another thing is that also you can know that V is equals to 0 means the short circuit, right? And I is equals to 0 means the open circuit. That's what we were saying, that when we increase resistance somewhere too much, like in mega ohms or something, the current is almost negligible. So that's what it means to make them open circuit. Okay. So how they will help us in the principle of superposition? Let's see. I am trying to solve a circuit, and then we will see, okay? So this is example 5.2 I'm doing, and so in this circuit, we have two voltage source. The conventional way of solving this circuit is that I do mesh analysis like that. And I will have I1 of t and I2 of t, right? And I will solve it using conventional analysis. And then I will compare that by, if I do it with the principle of superposition, whether my calculation agrees or not. So using KVL, for this network, I'll write just the equations. Okay. So I did not. Okay. So let's see. I don't know V1 and V2, okay? So it should be minus V1 of t plus 3k I1 of t plus 3k I1 of t minus I2 of t is equals to 0, which makes minus V1 of t plus 6k I1 of t minus 3k I2 of t is equals to 0. So this is the equation of loop 1. And loop 2 equation will be 3k I2 of t plus 6k I2 of t plus V2 of t is equals to 0. Here I should not do this. I should do 3k I2 of t minus 3k I1 of t. So it should be 3k I2 of t minus I1 of t. Okay. So it will become 9k I2 of t minus 3k I1 of t is equals to minus 2 of t, minus V2 of t. So I did solve this, and I just quickly write it. So it's, I do use the Gauss elimination method. And Gauss elimination method, I multiplied this with 3. And that will become then 18k I1 of t minus 9k I2 of t is equals to 3 V1 of t, and 9k I2 of t minus 3k I1 of t is equals to minus V2 of t. This will cancel. This will become 3 V1 of t minus V2 of t, and 15k I1 of t. I1 of t will become V1 of t by 5 minus V2 of t by 15. Sounds good?
Yeah.
Okay, so I have now I1 of t, right? I just don't want to calculate any other thing. I will just compare this that I will get the same equation or not with the superposition principle or not. Okay, so now I am going to apply superposition principle. Okay, superposition principle says to short circuit one of the sources to know the effect of another source. So first I will short circuit V2 of t. Okay, so short circuiting V2 of t will make my circuit as, I will draw it again. Right, so I will draw it again. Okay, I just removed the V2 of t from here. Okay, now I want to know currents, but I will not assign them the same name as I have assigned them before, because I want to differentiate this current from the normal currents, because this is not the same current. This is not the original current. This is the current that I am assuming after assuming that here there is no source. So this is not the original current of the original circuit, because in the original circuit there was a source. Here there is no source because this is my assumption. So I am giving another name to this current. Okay, that is I1 dash of t. So I1 dash of t I can find out easily by current division rule, right? So what I should say that first, that another thing is that R equivalent here is 3K plus 3K in parallel to 6K. So that will make it 3K plus 3 into 6, 3 plus 6 is 3 plus 18 by 9, 3 plus 3, no, 3 plus 2, which will make it 5K. So R equivalent is 5K here. Okay. So yes, so another way is that I said that I1 dash of t using Ohm law I said I1 dash of t is equal to V1 of t by R equivalent, which is V1 of t is, I don't know, V1 of t over 5K. Sounds good?
Yep.
So this is actually, so this is my I1 dash of t. So the second current I will found, like I want to find another current by using V2 of t after nullifying the effect of 1 of t. So I am doing short circuit V1 of t to know effect of V2 of t. Okay, let's do that. Okay, I'm not changing the directions of currents too. So this is my I1 dash of t, and this is my I2 dash of t. Okay. So as you know that I am comparing I1 dash of t. I want to know I1 of t. So eventually that's why I just found here I1 dash of t, because I don't want to know other currents just for brevity. I want to compare only I1 of t. So here also I want to know I1 double dash of t. So I just changed the name here too, because to differentiate with the currents. So if I use the same formula like I used before in the previous thing and find the equivalent resistance, it will be 6K plus 3K, 3K. Which will make it 7.5K. Right? So R equivalent will give me I2 dash of t, which will be equal to, because you know the current is in the opposite direction, so it should be minus V2 of t divided by R equivalent, which will be minus V2 of t by 7.5K. Sounds good, but I want to know I1 double dash of t. So now I know I do double dash of t. So how can I find I1 double dash of t? Any idea?
It's going to be the same between both branches, so it would be like half of what we have.
Oh, yes. Okay. That's another way. Or we can just, in the sophisticated way, we can say that this is a current division. So I'm just using current division rule. So it is I1 double dash of t is equal to I2 double dash of t, 3K by 3K plus 3K. And it will be equal to minus V2 of the t, 7.5K, 1 by 2. Okay, and this will become minus V2 of t by 50. Okay. I1 double dash of t. Sounds good?
Yep.
So now I will use the principle of superposition or additive property, and I say I of t is equal to I1 dash of t plus I1 double dash of t, which means that this is my I1 dash of t, and this is my I1 double dash of t. So I will just add them up and see that whether I am getting the same answer or not. So this is V1 of t by 5K minus V2 of t by 15K. Right? So this is the same answer I got here. Sounds good?
Yeah.
So it means that I can use superposition principle or to find out the total current. In superposition principle, I just have nothing to do but making the source's effect nullify to know the other effect of the source, like the effect of other source. But just remember that you are just nullifying the effect of source and not changing any other configuration of the circuit. Like you cannot change the current direction. You cannot change the resistor position. You are just changing the voltage sources, what you should say, voltage source or current source effect. So you will change their name, like the current or voltage name, but you are not supposed to change any other configuration of the circuit. Otherwise, all the circuit will change and the superposition principle cannot be applied. Okay? To just make sure that we understand this, I will solve another problem in which we have this effect of current too, so that we know that we are on the same page. So I am solving here example 5.4. Till now we are good.
Yeah, I think we're good
Okay,
on that.
let's do this. Okay, so this is our circuit now. And in this circuit, first I am applying superposition rule, and then I will compare it with any other normal rule to see that whether I am right or not. So first I want to nullify the effect of current source, making it open circuit. I will write it like that. Sounds good?
Yeah.
Okay. So I will just redraw the circuit to make it a little bit more simpler. Okay, and I'm saying that this is V1. Okay. I just turned this resistor towards here so that it looks more simpler to me now. And okay. Let's see. Okay. To find out V1. I am just trying to find out V1 first. So before that, okay, what I'm trying to do here is I will just find the equivalent resistance here and apply the voltage divider rule to find the V1. So equivalent resistance here is 8K in parallel with 4K, which is 8 into 4, 8 plus 4, 32 divided by 12, making it 8 by 3K are equivalent. So now in the circuit, I have 8 by 3K, 2K, and 6 volts. So this is V1, right? So because this is the V1 and this is the same voltage here. So V1, I will know by applying voltage divider. Which will become V1 is equal to 8 by 3K by 8 by 3K plus 2K into 6. That will make it 8 by 3K, 8 plus 6K by 3 into 6. So it will become 8 by 14 into 6. Right? And that will become what? 24 by 7 volts, right? So that is V1. Now I want to know V0, right? What should I do? So now I know this voltage, V1, and I want to know V0, this voltage. What should I do now? Are you here?
Yeah, we're here.
Okay.
Do you
So
do,
I thought I just disconnected again. I was like, oh my God, I did so much.
no.
Okay, so what do you think? What I did again.
Could we do the voltage divider between V1 and V0?
Yes,
And,
that's true. So, no. V1, no, between V1 and V0. We will do voltage divider. So this is connected in series, right? These two are connected in series, right?
yes.
So we will do voltage divider between them. But this V1 we have calculated here is the same V1 as this one. One question I think that is in your mind is that how come this V1 is same as this V1, right? So what we have done actually here, we have calculated the equivalent effect of this part of the circuit, right? We said that this part of the circuit's equivalent resistance is 8 by 3K. We know what V1 is. So now this is the V1 that we got. So this V1 is the same V1 here, and it's the same V1 here. So we will say, okay, how we can find V0. You can name that as V1 dash if you want, because because it's the assumption of the circuit. But as I just have to use V naught dash again, so I will just do V naught dash here. So my V naught dash is V1, 6K plus 2K makes it 24 by 7, 6K by 8K, making it 18 by 7 volts. So this is my V naught dash. V naught dash is what I'm supposed to calculate. I am supposed to know, because this will be the voltage that I will be getting after combination, and this will be the voltage that I will be finding out after nullifying the effect of other source. So now I know V naught dash is 18 by 7 volts by open circuiting current or nullifying the effect of current source. Okay, so now I want to nullify effect of voltage source, keeping the current source in the circuit. Okay, so this is my circuit. So how should what circuit should look like when I will nullify the effect of voltage source?
It'll look the same, but there'll just be a wire where the voltage source was.
Yes, yes, okay. So let's see. Okay. So this is my circuit now. Okay, after nullifying the effect of current voltage source, I am just replacing it with the single wire, and then my circuit will be this. Okay. Okay, sounds good. So I want to simplify the circuit. I will just do a parallel combination of this part, and this will make my circuit a little bit more simpler. So I'll just do this. Is it 6 or 2 milliamps? Okay. Two milliamps, okay? So my R equivalent here is, so you can use any method to simplify your circuit, okay? To find V naught dash or V naught double dash, it's up to you. There is no restriction on that, but just follow the principle of superposition, okay? So it will become 4 by 3K. So this is 4 by 3K. So to find V naught double dash, okay, so to find V naught double dash, what I will do is I can find the current in that branch, okay, which I can do by applying voltage divider rule. So current in that branch will be Is it right? Is the formula of current division is right or not?
Yeah, it looks right.
Okay. So it will become 5 by 7 milliamps. Okay, I naught double dash. So this will make my V naught double dash simpler, and that will become 6K multiplied by I naught double dash. 6K multiplied by I naught double dash, and this will be 30 by 7 volts. So that is my V naught double dash. Now, by using rule of superposition, I will say that V naught is equal to V naught dash plus V naught double dash, which is equal to 18 by 7 plus 30 plus by 7. So 18 by 7 plus 30 by 7, which will make it 48 by 7 volts. So that is V naught I have, okay? Now, I want to confirm that this V naught is same as V naught, which I will get from any other method, okay? So I am using mesh or loop analysis to know that. Okay, so maybe you don't have to, verify every time. I'm just verifying it because it's a start and we want to know whether it apply to all kind of independent sources or not, okay? So just remember that I mentioned that I am applying superposition rule only on independent sources. So if you think that you are good, you don't have to verify it every time, okay? But I'm just doing it for the sake of that it's a start, so we should be doing it. So this is my original circuit, and I will be using it using mesh analysis, okay? So I am doing I1, I2, and I3. Okay. Okay. Let's see. I will write equations. So my equations are -6 plus 4K I1 minus I3 plus 2K I1 minus I2 is equals to 0, right? Then my I2 is 2 milliamps, so I don't have to write the equation in the second loop. My I3 is 2K I3 minus I2 plus 4K I3 minus I1 plus 6K I3. Am I good? Can you hear me?
Yeah, that all looks good.
Okay. Oh my God, it's so, just a minute, let me see. Derek, are you here?
Yeah, I'm here.
Am I good?
Yeah.
Thomas, am I good? Sarah, are you here?
Yeah,
You good?
yeah, I am.
Okay. Sounds good. Okay. So I used mesh analysis and I did. Okay. So let's see. It's just a matter of that we have to solve it and we will. So I am just trying to simplify the scenario by replacing wherever I have I2, I will replace it with 2 milliamps. Okay. So let's do it. First, I am doing with this. Okay. Okay, which will make it 10, 6K I1 minus 4K I3. Right, so this is my first equation. My second equation will be so if I just add I3 is 2 plus 4 is 6, 6 plus 6 is 12, K I3 minus plus 4K I1 and it's equal to 4. Okay, so this is my second equation. So what I'm trying to do is I want to get rid of, okay, here I actually got rid of I3. Okay, so to get rid of I3, I just multiplied this by 3 and which will make it there is one mistake here. Okay, sorry, this should be minus because this is minus 4KI1, okay? So this should be minus, okay? So this is 14KI1 and I1 is 17 by 7 milliamps. Okay, now I just replace this somewhere to find my I3. So I am just replacing it in this equation. That will make it 6K 17 by 7 minus 4K I3 is equals to 10. So this mesh equation is for first loop. Okay, so it will become 102 by 7 minus 4K I3. So what is equal to 102 by minus 70? 32, right? 32 by 7 into 1 by 4 is minus. I3 is equal to 8 by 7 milliamps, which is I3 is equal to 8 by 7 milliamps. Sounds good?
Yes.
Okay, so now V naught is 6 into 8 by 7 milliamps, which is equals to 48 by 7 volts, 6K. So this is our V naught, which is equal to V naught here. Okay, so what we did, we said that V naught that we have found using superposition rule is the same as V naught we can find from any other rule, right? So that's why our superposition rule can be applied on the current source or on the voltage source. Like it's just if we apply the rule right, we should be fine. Okay. Are we good?
Yeah.
Do we have any questions? Thomas, are you there?
Yeah.
Okay, so we are good for today then, and see you guys in the next lecture. Thank you.
Have a good
Have a
weekend.
good weekend.
You
Bye.
too.
Have a nice day.
You too. Bye.